So welcome back. Happy Monday. Our quick look at the calendar tells us that today we're going to talk about Fibonacci numbers and nature. And I just want to highlight that this is our last day of new material before the upcoming test. On Wednesday is our review day for that test, which is coming up on Monday. Okay, second test is coming up Monday, 1 week from today. That test is not cumulative, so we're not going to see the stuff about voting and weighted voting theory that we did in the first test. It is only on the material since the first test. Shh. Everybody clear on what's fair game for the test? It's apportionment and then the stuff with sequences. So it's coming up a week from today, and it is not too early to start studying for that test. As usual, there are practice test problems in the packet, along with videos on YouTube. Questions on the calendar? Okay, and one other thing about the calendar, which won't affect us, but tomorrow is Veterans Day, and there are no day classes at GCC. So if you have Tuesday classes tomorrow during the day, do not go. All right, so on page 45, we're just going to remind ourselves that at the end of last class, we talked about this bee problem, and we traced the family tree of one particular bee based on this, I don't want to call it strange, but different than human way that male bees and female bees are created, right? They're created differently, and the female bees had two parents, but the male bees had only one parent, and it was always a female, okay? So we did this, and we ended up with this particular list of numbers that you guys had. So I'll fill in the next few, 5, 8, 13, and then 21. And then we started to look at some patterns in that list of numbers. And can somebody give me like a plain English way of describing how you get the next number in this list? Add the previous number. So add the previous number to what? To the number before that, right? You add the last two numbers, and that gives you the next number in the list. And so on the very next page, we will we'll write that down symbolically. So let's go to number 2. Can we get Matt to read number 2? Top of 46. Okay, you can pause there, but remember we're just numbering the terms in the list. So for example, what is the 6th term in this list? 8. And so this equation is just saying the 6th term in the list is 8, okay? All right, so let's keep going here. F9, F10, and 11. Did we find those? F9, how much is F9? Is that the 9th one? Yeah, because F8 is the 21, that's right, and so F9 is 34. So go ahead and write down F10 and F11. Take a moment to do this calculation. I don't know that you have these numbers already, maybe you do, but use a good notation. Don't just write the answer, but use the sequence notation. So what is F10? That's 55, and F11, 89. Good. Okay, so moving to number 4, talks about writing a recursive rule for the Fibonacci numbers. Fibonacci was the name of a mathematician back like 1200 AD or so. And this list of numbers came out of a problem in a book that he was famous for writing. And this problem in the book was like the bee problem. It was just in an appendix. It wasn't like a book about this bee problem. It was just one little tiny part of a much larger book, but that one problem made this guy famous. So, so we call the numbers after him. So the recursive formula, let's write it down. Normally, it would look like this. You guys remember we would write this beginning for just about every recursive formula we would write? So it's not complete, but at least it's a start. It says if you want to get a certain number, you take the n minus 1, the number 1 before, and what else do we do? Add it to the one that's 2 before. F n minus 2, that's it. That says take the number that's 1 earlier plus the number that's 2 earlier, and that gives you the next number. So that's our recursive rule. Of course, the recursive rule won't get you off the ground unless you have the starting number or two numbers in this case. We actually need two numbers. So the first two numbers are both ones. They're called the seeds, and we imagine this tree kind of growing based on that. So there is an explicit formula actually that will get you the Fibonacci numbers directly. Like in order to get the 20th Fibonacci number, we would need to get the first 19. There is a way to get the 20th directly. It involves something called Benet's formula, which you can look up. It is quite complicated, but we're not going to worry about it. But I would like us to be able to answer questions like this. Suppose that I tell you that the 39th Fibonacci number is this 6 million and change, which it is. I'm not just making that up. And I tell you that is there another digit hidden behind this word and? No, something. Oh, you guys can see the 6, no problem. Oh, okay. So it's not 6 million, it's really 63 million. Yeah, all right. Something happened when we brought this guy over to Smart Notebook. Okay, like that? Okay, so suppose I tell you that the 39th Fibonacci number is 63 million and change, and the 40th Fibonacci number is 102 million and change. I'd like you to be able to find F41 and F38. Let's give this a shot. So if you want to find the 41st number, Zeke? Go ahead. F0, good question. We're going to come back to that after we do these two. What was your other question? We'll answer that after we do the 0 question. Okay, good questions. All right, how do I find the 41st number given the 39th and the 40th? Tony? Yeah, how do I get the 41? Do we subtract them? I don't think we want to subtract to find the 41st. I think we want to add these two numbers because our basic rule for the Fibonacci list, right, you just add the two previous and that gives you the next. So we're just going to add these numbers up. So it's the 40th number plus the 39th number. So somebody with a calculator. Louder, Sam. Okay, that seems reasonable, 165 million. Okay, so that's that one. But what about the 38th number? So before we say the answer out loud for how to calculate it, any questions on calculating the 41st? Easy, right? It's just add the two previous numbers. But to go backwards in the list, like if I just wanted F38, I guess one way to get it would be to take F37 and add F36. Don't write it down, but this is the basic way to get the 38th number, right? As you add the 37th and the 36th. What's the problem? We don't know either of those. And so there's got to be some other way. So we're not going to use that. I think what we're going to use is this. Some of you might just feel intuitively what we need to do with these two big numbers, but in case you don't, I'm just going to look at the definition for the 40th number. How would you get the 40th number the basic way? You'd take the 39th and add the 38th, right? That's the definition for how to get the 40th. But a couple of these numbers we know, right? F40 is this guy, and F39 is this guy. So what are we going to do with the 40th and the 39th? We're going to subtract them, right? I mean, basically, you're taking that F39 and subtracting it to the other side. So like I said, some of you might intuitively have known just subtract the numbers, but in case you didn't, it does fall out from this basic equation. It says you want to get the 38th, great. Take the 40th and subtract the 39th. Okay, somebody with a calculator? $160. Okay, that seems reasonable. Okay, so just a brief blurb about this guy Fibonacci, whose name is attached to this particular this particular set of numbers. So, so his real name was Leonardo of Pisa, Italy. And one thing that he did in his travels is that he learned about Arabic numerals, which are the numbers that we use, like 18 and 29, the way that we write them there. Those are Arabic numerals. What number is this right here in Roman numerals? X, V, I. Do we know these Roman numerals? X is 10, V is, and the I's 1. What about this guy? X, X, I, X. Yeah, how do we get 29 out of that? Yeah. If you see a small number coming before a bigger number, it means you're subtract, actually. 10 minus 1. So that part right there is 9 plus the two 10s in the front is 29. So 18 plus 29 we would do normally this way. Can you imagine trying to do 18 plus 29 the Roman numeral way? Or like there's no lining things up, right? Like we take for granted that, oh, you just add these guys, and if you have to carry something, no problem, just carry it and then add these guys, right? It's a convenience that we don't even think about because it's all we know. But imagine doing even the simplest arithmetic in Roman numerals where we don't have this nice placeholder set up. So one of the things that we can thank Fibonacci for was bringing these Arabic numerals to Europe and then eventually here. So Fibonacci is most famous for that book that I told you about. So it's the Liber Abaci. Liber meaning book and Abaci meaning abacus. Like I said, 1200s AD. And so let's get, Jen, can you read that quote, a certain? Okay, so this was the problem that led to this guy's name being attached to that sequence of numbers. So let's give this a shot. You don't need to write this down, but we'll just take a little pause here. So we're going to write down the number of months that we're in, and then we're going to write down the number of adult pairs of rabbits, and then the number of baby rabbits. So they're babies for 1 month, is what it says in the problem, and then the total pairs. Okay, so at the start of this problem, it says that we put, what do we put? A pair of rabbits into this enclosed area. And so at the start of the first month, let's just put a 1. It doesn't really say whether they're adults or babies. Let's assume that they're newborns. So no adults, 1 pair of baby rabbits there. And so the total number of pairs of rabbits then is 1. And then it takes 1 month for baby rabbits to become adult rabbits. And so when we come over here into this next month, how many adult pairs do we have? 1. And it's, what do you think? Do they have a new pair yet? Or it doesn't seem like it from my reading of that. Is that they become, they don't become reproductive until they're actually adults for a full month. So how many total pairs here? 1. Okay, and now things are going to start happening. You know, there's some nice music and some wine, and rabbits do what they do, and then what happens here? So how many adult pairs do we have? Still the 1, but there we go. And so then we have 2 pairs. All right, let's keep track of all this now. 4th month. This pair of rabbits right here becomes adults, which means 2. Is that pair going to produce a new pair? No, but we do have the original pair that is going to churn them out once a month. So 3. All right, we're going to do 1 more. Okay. How many pairs of adult rabbits will we have? 3. It's the 2 that are already there plus this 1 pair of babies that becomes adult. 3 adults. But how many newborns? It's 2, because in the previous month you had 2 pairs of adults that were waiting there. 2 there, and altogether 5. And have we seen this collection of numbers before? 1, 1, 2, 3, 5. Yeah, so this is the same Fibonacci list. So like I said, it wasn't in terms of B's, but somehow this setup is equivalent to the B setup. Yeah. The rabbit incest always bothered me about that part. All right, next page. So it turns out the Fibonacci numbers appear pretty frequently in nature. Your pictures are way too small to see that there are numbers on these petals of the flower, and I could barely see it up here. You guys can't read those numbers on your page, can you? Yeah. So can you? So can you read that number right there? This one right here. So 13, and they're all counted out. Starting just to the right of that one is number 1. So how many petals on that one? 13, which happens to be one of the Fibonacci numbers. Okay, so what? I think the biggest one is there. I don't know if you can. Yeah, that does say 21, and they're all labeled 1 through 21, which is another Fibonacci. And then that guy right there is 34. Okay, so I don't know. Do you buy it? Do you buy that like these numbers very naturally appear, or was it somebody who just like kept picking daisies until he found one that had the right numbers on it? There actually is a little bit of biology that I've heard about that would indicate that yes, indeed, the Fibonacci number should appear in here, and it has to do with, like we all kind of want our own space, right? And so like if you end up buying a house, you get like a fence around your yard and you have some space that's carved out for just you, right? And the theory is that these petals also want some space. And so if there's a new petal that's going to come into the neighborhood, the new petal is going to come in such a way that they get as much space as possible. They can grab as much real estate without banging into the neighboring petals. And there's something about maximizing the amount of real estate that each petal has that leads to these specific numbers. I can't give you more details because that's my complete understanding of the thing. But in any event, it compels me that, hey. Oh. Anyway, it was more than just like some magical thing that appeared out of no place, at least from what I saw. This is the bottom of a pine cone. Again, you probably can't see, but the little, I don't know what those things are called on the pine cone, but whatever those things are, you can kind of see them spiraling out in one direction or the other. And it turns out if you count, so like that's one spiral, and then here's another spiral. And if you count all of these in this picture, you'll actually find a Fibonacci number of spirals coming from the center. I don't know where the biggest number is. You can't read those, can you? Yeah, it might be 8. Maybe 8. And then if you look at the same exact diagram and then you draw these shorter spirals going the other direction, I think it's that number up there, might be 13. Yeah. Yeah, it's a blurry 13. And then this is really going to kill your eyes. So this is a close-up. And again, you can kind of see these things kind of spiraling, but I think the biggest one is that one. And then is it up there? Is that a 34? Yeah. Okay. So we're going to do things a little bit differently than usual. What you're going to do is group activity, but then we got to come back together and conclude things for like the last. Yeah, so it's like a group thing, and then we're going to come back together, and then it's another group thing. So here's what you're going to do. You're going to fill in, shh, everybody up here, you're going to fill in the first 20 Fibonacci numbers. When you get to number 10, check with your neighbors because we want to make sure everybody's got the same number, and if you make a mistake, you want to find it early rather than late. So you're going to fill in the first 20 Fibonacci numbers, and then you are going to divide them in the way that I have written in the second column of this table. So for example, let's just do the first few together. What do we have? 2, 3, 5, 8, 13. Yeah? And I want to take a look at this one right here. F5 divided by F4. Can we do that one right now? F5 divided by F4 is what divided by what? It's 5 divided by 3. Everybody see it? F5 divided by F4. So you can do it by hand because the number is small, but you're going to be using your calculator quite extensively here. But what I need you to do is write down 5 digits. You're going to round after the 5th digit after the decimal point, okay? So don't just write 1.7. You're not going to get enough. We're not going to get what we need if you just round too early, okay? So for 5 digits for all the division stuff. Yes, regular. And then we'll change it to a 7 on that last guy. Thank you. Yeah, so give me 5 digits after the decimal point, check with each other, and then we'll come back once everything's filled in. So what did we see appear to be happening in that division column? Were you expecting that it would be the same number over and over again? There's nothing in here that would indicate that, like, if we just keep dividing all these crazy Fibonacci numbers, that we should be approaching anything, right? But somehow it seems like we're honing in on this number. And I'm not saying it's the prettiest number, this 1.618, but it seems like we're honing in on this one number. And that one number is quite famous enough to have a name. So let's take a look on the next page. Number 8, I think we're up to Jeff. Yeah, phi or phi. So that's the golden ratio or the golden number. It's got a bunch of different names. And it's so important in math that we have a letter that we assign to it. What other really famous number in math has a letter assigned to it? Pi, right? You guys are comfortable, like pi is technically a letter, but we've assigned it to this number that has to do with circles, right? So this guy right here, phi, is just some other Greek letter, but we assign it to that magical number right there, that 1.618. Okay, so let's see if we can use this idea, this phi business. So I can't read this on my page. What does that say? F 499. Okay, so F 499 is this 8.6 times 10 to the 103. So you don't need to rewrite this, but I just can't see it. Okay, so that means that's the 499th Fibonacci number, right? Long list, very, very big number. I want to know what the 500th Fibonacci number is. Can we use our basic Fibonacci equation that says take the 2 previous numbers and add them to get the next one? No, we don't have enough information, right? We only have 1 previous number, not 2. And so what are we going to do with this number? Well, we're going to make use of the fact that if you take the 500th Fibonacci number, whatever it is, and you divide it by the 499th number, what do we think we're going to get, roughly? 1.61803, right? That's what we would expect to get because that's what the table seems to indicate. It's not going to be perfect. No, it won't be perfect, but it should be pretty darn close. So a little bit more algebra here. What do we do to both sides of this equation to get the F500 by itself? Yeah, can't we multiply both sides by the F499? Multiply the left side by F499 to cancel. So both sides multiplied by F499, a little bit of algebra here. They go away there, and we just see that the 500th number is about 1.6 times the 499th number. Okay, fair enough. Let's see if we can do that calculation. So we're supposed to take this 1.618 and multiply by that crazy thing over there. 8.6168 times 10 to the 103. Now, it makes sense because all we're saying is that you want to get to the next Fibonacci number, just keep multiplying by this magical phi thing, and it should get you pretty close. Now, the problem here is that we can't type that into the calculator directly, at least not most calculators. That 103 is too large of a power for most handheld calculators to deal with. So what we're going to do is we're just going to type in the decimal things together, and then we'll deal with the 103 at the end. So somebody with a calculator, what do we get when we do this 1.6 and all that times the 8.6? Okay, can anybody confirm that number? Sarah, did you get that? 13.9. Was there a 0 in there, Sarah? Anybody get either of these numbers?
I got it.
right, I don't trust you guys as far as I can throw you. Let's see. 1.618 times 86168. Okay, and Sarah, you might have done the 03, which is probably a more accurate answer than I have because I didn't do the 03. Okay, so 13.9422. And what are we missing on this guy? Times 10 to the 103, agree? Right, it was just sitting there, times 10 to the 103. So we chose this really massive number so we'd have a moment to practice with scientific notation. Zeke, put that away. So this number is not currently in scientific notation, this 13.9. What's wrong with 13.9 that says it's not in scientific notation? Do we know scientific notation? The decimal is not in the right spot. Where should it be? It should be 1.39, right? So let's see if we can fix this. So this is equal to 1.39422. And then we got to make sure we go the right way. We know we differed by 1. So it seems like the natural choices are 102 and 104. Did you make the 13.9 bigger or smaller? Smaller. So to balance the scales, we'd better make the 10 bigger, right? Like you can't just make the entire number smaller. So 104 is good. And by that or no? We made the 13 smaller, so you got to make the 10 bigger to make up for it. Okay, and so I'll show you this on the calculator real quick, this whole 1.618. Suppose that we start with one of the Fibonacci numbers. What's the 10th Fibonacci number? 55. So I'm going to multiply that by 1.6, what was it, 1.61803? Okay, what's the next Fibonacci number after 55? 89. This is not going to be perfect. It should be close. Close? Okay, I'd be quite comfortable saying, okay, I think it's 89. And then if we take 89 and multiply it by the 1.61803, what's the next one after 89? 144. Really close, right? So it's not perfect, but it's going to be really close. And the further down you go in the list, the closer the approximations will be. Okay, so we're going to skip over this number 9. And I'm just going to jump down to this scary phrase from your past. Raise your hands if you know the quadratic formula. Yeah, dust off the cobwebs. How does it start? Negative b, plus or minus. We remember this thing?
Negative b.
Ashley's shaking. Let's stop. We don't want to traumatize anybody. So in any event, if you use the quadratic formula, on a particular equation, you eventually get down to this number, this 1 plus root 5 over 2. And I will tell you that that is the exact value of our golden ratio. So if I type in 1 plus root 5, divide by 2, then we see our old friend, but in fact, it's perfect. That 1 plus root 5 over 2 is the exact value of this magical number, right? We were approaching it in the table, but in radical form, it's perfect. The 5 comes out of an equation that I didn't write down. Yeah. Okay, let's go to 11, Zeke. 11. Okay, so that 1.6 number apparently is appealing to the human eye, and so if you know what you're looking for, you might see it kind of everywhere. So I guess what we're saying is that I don't know how long how long is like a credit card normally, like 2 inches maybe? Sure. About 2 inches. So the idea here is that this is about 1.6 times the other side. So if we make something where it's 1.6 times the shorter side, we're making something called the golden rectangle. So you see it there. Like if you, just go home and like start measuring things and just see if you can find some sides which are about 1.6 times other sides, and I bet you'll be able to find them. So there's a Mac, and this is the, I don't even know what I'm looking at in the middle picture. Oh, I think it's probably something like that. Like if this is 100 feet, the top part of the spire, then maybe this is like 161 feet, the bottom part. You think it's the boat?
I believe you.
You shouldn't believe me because I don't know what I'm supposed to look at in that picture either. Let's see what's happening here. So if you look at like the rectangle that's on the front of the, it's called the Parthenon or the Acropolis. Which one is that? Parthenon. So like the idea is that folks studying architecture have looked these numbers up and the measurements, and there's a lot of 1.6s floating around. Same thing here. This one seems a little bit like hocus pocus to me because I could draw any rectangle around the Mona Lisa, and I don't know if there's anything natural about that particular one, but that one anyway is a golden rectangle. Okay. So on the next page, Fibonacci group work, see how far you can get.